Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll look at the angle, sum, and difference formula. So there's one for sine, cos, and tan. So I've just given you the angle sum formula. There are also formula for differences. So this would be sine of x minus y, cos of x minus y, and tan of x minus y. So I'm not giving them on this video. We're just going to do them in the exercise because to get, for example, sine of x minus y, it's a very simple manipulation of this formula. But let's look at how I might use it. So let's say I had something like sine of 3a plus 2b. So we're going to expand this using this first formula. So all it is, it's just sine of the first thing being added, cos of the second thing being added, and then you switch them around. So it'll be sine 2b cos of 3a. That's easy as. Let's look at an example now involving cos. So let's say I have cos of 4y plus 2z. So then that is just cos of the first. Now cos is different. It's cos of the first times cos of the second. I had a friend in school who used to always say cos loves itself. So that's cos of the first times cos of the second. And then even though this is a plus in here, it's a subtract. We subtract sine of the first times sine of the second. So this is just how we expand sine, cos, or tan when we have two angles being added together. So let's use the tan one. Let's say I want to find tan of 2 theta. So of course 2 theta is just theta plus theta. So if I substitute that into here, I just change x and y to theta. So I get tan theta plus tan theta over 1 minus tan theta times by itself. So remember, we write that as tan squared theta. So tan squared theta means tan theta times by itself. And of course, we can simplify that to 2 tan theta over 1 minus tan squared theta. Okay, so that's just getting used to the formula. What do we actually use this for? We can actually use this to find some more exact values. We came up with exact values for sine, cos, and tan of like 30, 45, 60, 90 and all that. So these formula will actually allow me to find exact values for sine, cos, and tan of angles that are multiples of 15. So I'm going to go through how to find sine of 105 using this formula. So what I want to do is write this of sine of two angles for which I know their exact values. So since I know sine 60 and 45, I can write this as sine of 60 plus 45. So using the first rule up here, that's just going to be sine of the first, cos of the second, plus the other way around, sine of the second, cos of the first. So I know sine of 60 is equal to root 3 on 2, and cos of 45 is equal to 1 on root 2. So we have sine 60 times cos 45 plus sine of 45 by cos 60. So let's just simplify this. So root 3 times 1, 2 times root 2 gives me the first fraction, and then the second fraction, 1 times 1, 2 times root 2. So that just is root 3 plus 1 over 2 root 2, okay? So we could rationalize the denominator by timesing by root 2, but this has given me exact value of sine of 105. So I could also do something similar to find cos or tan of 105. In fact, I could do this for any angle that's a multiple of 15. I could find sine, cos, or tan of 15, of 75, so on. I can come up with more exact values because of these rules. So on the next slide, I'm just going to go through a quick proof. Okay, so we're going to prove the sine and cosine identities that were on the previous slide. Sorry, I have to do this. So what we have here is a rectangle. Enclosed in it is a right-angled triangle. So we've called this side here 1 and labeled our angles beta and alpha. So what we're going to do is come up with expressions for the lengths of sides, and that will allow us to prove what we need to. So let's call this side here x. So using basic trigonometry, we have cos of beta equals adjacent over hypotenuse. Of course, dividing by 1 doesn't do anything, so we can rub that out. This side here, x, is the same as cos of beta. So I'll replace this and call it cos of beta. And similarly, this side here will be sine of whatever beta is. So now we're going to find an expression for this side here. I'll call it y. So using trigonometry again, this is the adjacent. So I say cos of angle equals adjacent over hypotenuse. Of course, I can get y by itself by just timesing each side by sine beta. So this side here, y, I can rub this out and I can write it as sine beta cos alpha. So if I do something similar in the bottom triangle to find this side here, using this right-angled triangle here, I would get that that side is sine alpha cos beta. I do it exactly the same way I found this side here. So I'm just going to rub that out now. So we've found an expression for this side of the rectangle. Now we're going to find an expression for this side of the rectangle. So note, this angle here is alpha plus beta. So because they're alternate, this one here will also be alpha plus beta. So if I want to find an expression for this side here, let's call it x, I can just use trigonometry again. So to find x, it is the opposite, and I also have the hypotenuse. So what I get is sine of the angle is equal to opposite over hypotenuse. Once again, dividing by 1 doesn't change it. So I can simply rub this out. X is sine of alpha plus beta. So I found that this side here is sine of alpha plus beta. So what that means is, because this is a rectangle, this side and this side must be equal. So sine of alpha plus beta must be sine beta cos alpha plus sine alpha cos beta. That's exactly what I showed on the previous slide. It's just I used an x instead of alpha and a y instead of beta. That's how you show that. So rubbing out this working out here and this working out here, I can do the same for the other two sides. This side of the rectangle and then this side of the rectangle. So using trigonometry in this small right-angled triangle here, if I want to find this one, I use cos again, and I can find that this is cos alpha times cos beta. That is the expression for this side here. So if I use trigonometry to find an expression for this side here, it's just going to be cos of alpha plus beta. So that's just this side here. And again, I can use trigonometry to find an expression for this side here, and I would get sine alpha times sine beta. Okay, so let me know if you want to know more about the calculations. It's just using simple trigonometry, SOHCAHTOA. So because this is a rectangle, this side and this side must be equal. So what I have is cos of alpha times cos of beta must be equal to cos alpha plus beta plus sine alpha sine beta. I know that's a really complicated equation, but it's essentially saying this side and this side must be equal. So I can make this the subject of the equation by just subtracting sine alpha sine beta. And if I do that, I get cos of alpha plus beta is equal to cos alpha cos beta, and I've subtracted from both sides sine alpha, sine beta. Okay, so that's proved this equation which we saw on the previous slide. Once again, I used x's and y's instead of alphas and betas. So I've proved it for sine, that sine alpha plus beta equals these two things added together. I've proved cos alpha plus beta equals this minus this. These were on the previous slide. Now, the rule for tan actually just follows from these two. So I'm not going to prove tan here, but I know that tan of alpha plus beta, remember tan is just sine over cos. So it would be sine alpha plus beta over cos alpha plus beta. If I wanted to prove the rule for tan, I would just use the rule for sine and the rule for cos, and I could just rearrange it to get the formula I had on the previous slide. So again, I'm not going to go through the proofs for the difference formula. We'll just look at that in class because they're just a special case of the addition formula. All right, please let me know if you have any questions. This has been the luckiest maths teacher in the world. Have a great day.